Welcome to this section of the notes. Today's objectives are to use sigma notation to write and evaluate a sum, to understand the concept of area, to approximate the area of a plane region, to find the area of a plane region using limits, and to evaluate an area with the graphing display calculator. Integrals is all about finding areas, so this is where we will really start to work with that. Sigma notation is something you've probably seen in the past. It's a way to express a large sum in a compact form, and the key elements is that if we have n terms here called a1, a2, a3 all the way to an, we can just write it as the sum s, this is the Greek letter s, sigma, the sum of ak, k going from 1 to n. There's a few formulas. Those that are really important are the first one here. If you add a constant number n times, then you'll have c times n, or we should rather say n times c. And if you add 1 plus 2 plus 3 plus 4 plus 5 all the way to n, the sum will be n times n plus 1 over 2. Example that's a little bit more complicated, the sum from I equals 1 to n of I plus 1 over n squared. It's important to realize here that I goes from 1 to n, but that n is a constant. So n squared here can actually be factorized, and we can rewrite the sum as 1 over n squared times, open parenthesis, the sum from I equals 1 to n of I plus 1, which can be broken down into two sums, 1 over n squared times the sum of I plus the sum of 1. And now we recognize the two formulas we've pointed out earlier. The sum of I equals 1 to n is n times n plus 1 over 2, and the sum of 1 plus 1 plus 1 plus 1 n times is n. We distribute and put everything together, and the answer is n plus 3 over 2n. So the big thing with integrals is to find areas under curves. Here's an example: f of x equals 1 over 8 times, it's a cubic function, and we are looking for the area between x equals 1 and x equals 5. Vertically, the area is bounded by the x-axis and by the function f. There's different ways of choosing rectangles that fit the area well. We'll talk about the first one now. If we pick the middle of each interval, so here the intervals are from 1 to 3 and 3 to 5, we can choose f of 2 to determine the height of our rectangle. Here the midpoint of the interval is 4, so we pick f of 4 to be the height of our rectangle. Clearly this is too much and this is not enough, so the area of these two rectangles is not exactly the area under the curve, but it's a fairly reasonable approximation. The area of this rectangle is base times height, 2 times 2.4. How did I find 2.4? As I said, we are only looking at this example geometrically, so I'm just staring at this point here, and it's 2.4. For the second rectangle, the base is 2 again, and the height is kind of 3.1. It's around here if you look carefully at your own page. So the area of the second rectangle is 2 times 3.1, and if we add these two areas, 4.8 plus 6.2, we get an approximated area of 11. But we can do better. We can choose 4 rectangles, and I invite you to pause the video now and to really try yourself doing base times height 4 times in a row. Look carefully at the height of these rectangles. Notice how we've picked the midpoint every time to choose how high the rectangle is, and then press play again. This is my result. I found that the area of the first rectangle was 2.1. 1 times 2.1. The area of the second rectangle was 1 times 2.7. The third rectangle 1 times 3.2. And the fourth rectangle 1 times 2.8, which yielded an area of 10.8. So slightly lower than the first approximation with only 2 rectangles. But we can go further, and once again, even though it looks tedious, I would recommend that you really try yourself, spend a few minutes adding all these areas. There's 16 rectangles, find where the midpoint is, find the height of each rectangle, find the width of each rectangle, and add all these areas up. Then please press play again. So the base of all of these rectangles is 1/4, and I estimated that the first rectangle has a height of 2, the second rectangle has a height of 2.05, etc., and I got 10.5775. In a week or so we'll find the exact area of under the curve here, and we'll be able to compare our estimations with the exact answer. But we can already see now that with 16 rectangles, our approximated area is definitely going to be very close to the real area. So the previous example used midpoint rectangular approximation. This is shown again here. To choose the height of each rectangle, I picked the midpoint of the interval, and f of that point was the height of the rectangle. So we chose the midpoint of each interval to determine the heights of rectangles. But we can choose other methods, and we will focus on two especially, the left rectangular approximation method and the right rectangular approximation method. In the exercise below, use the left rectangle approximation method, LRAM, to approximate the area between the x-axis and f of x equals x squared sine x on the interval 0, 3 using 6 rectangles. This is what the graph looks like, so we'll try to find the area between x equals 0, x equals 3, and it goes vertically here, and then the curve and the x-axis defined the boundaries of the area we're studying. I graphed the function roughly. We will see later on that actually this rectangle should be higher than that one, but it happens when we do sketches. What's really important to notice is that here my rectangles are defined by the left endpoint. So for instance, this rectangle here, how did I choose the height? I picked the left endpoint, and f of that point gives me the height. In the table below, I have intervals that are from 0 to 1/2, from 1/2 to 1, 1 to 1.5, and so on. So the width of each rectangle is going to be 1/2, and the first rectangle has a height of 0. If you punch in your calculator f of 0, so 0 squared times sine of 0, you get 0, and therefore the first rectangle has an area of 0. Please spend a minute completing this table, and then you can press play again. So this is the table when it's completed. The width of each rectangle is 1/2. F of 1/2, this is 1/2 squared times sine of 1/2 is 0.120. Therefore the area, base times height, or width times height, equals 0.060. We do that for each of the 6 rectangles, and we get a total approximation of 5.292. Remember to keep more than 3 decimals here. Keep more than 3 decimals here too when you want to add them all up in the end and have an answer that is correct to 3 decimals. If you round to 3 decimals here, you may have an error in the end. Obviously, there's also a right rectangular approximation method, but I'm not going to give an example here. Something that is sometimes confused with LRAM and RRAM is the lower sum and the upper sum. A lower sum is a sum obtained by adding the area of rectangles that are all under the curve. So here we have a curve and all these rectangles are under the curve. But notice how I've picked rectangles that are sometimes based on the height on the left side of the rectangle, left side, left side, left side. But after a while I need to pick the right side of the rectangle to define the height, or else my rectangles will go above the curve. An upper sum is a sum obtained by adding the area of rectangles that are all above the curve. So this time I picked the right rectangular approximation method here to make sure that I'm above the curve, and then I had to switch to the left rectangular approximation method. By the way, you can see in this example that it doesn't matter that all my rectangles have the same base. This one is really tiny, this one is very large. It's okay. It's still called a lower sum or an upper sum. The key concept here is to realize that the more rectangles we have, the more the area will look like the actual area under the curve. As the number of rectangles increases, the area of the rectangles approaches the area under the curve. Actually, the area under the curve is equal to the limit as the number of rectangles approaches infinity. This is true for any of the three rectangular approximation methods we've seen above. There's one thing we need to specify here that's not written, is that the base of all the rectangles needs to approach 0. We could have a rectangle that's not approaching 0 and still have an infinite number of rectangles. So it's not quite enough to say that there's infinitely many rectangles. We need to specify that the base of every single one of them is also approaching 0. With your calculator, if you have a TI-84, you can follow these instructions. If you have another calculator, you can easily find online how to find the integral. Try it with this function here, f of x equals 10x squared times e to the negative x. Find the area between the x-axis, the curve, and the vertical boundaries x equals 1 and x equals 4. And you should find a equals 13.632. Very useful, crucial in AP exams for all the calculator sections. So we'll now revisit all the objectives. The first one was to use sigma notation to write and evaluate sums, so we've seen that. The concept of area bounded by x equals 1, x equals 5 here, bounded by the x-axis and the curve. We've seen that we can approximate area of regions by choosing rectangles. We've discussed that the actual area is a limit as the number of rectangles increases to infinity with the base of the rectangles approaching 0. And we've seen that we can find with our calculator the area under a curve by just punching in the correct series of buttons.